Well, welcome to the Mobile World Congress discussion zone. And right now, we're going to have a presentation on complete RAN virtualization, the foundation for mobile edge clouds, 5G, and even beyond. And to do that is speaker Aaron Bello, who is the CMO of ASOCS Networks. Aaron, over to you. Thank you.
Thank you so much. Hi, everyone. Thank you for joining us here in the HPE discussion zone for the presentation. As mentioned, we'll discuss today complete RAN virtualization and as the foundation for open mobile edge clouds toward 5G and yes, even beyond. What we are seeing is the carriers are expanding into new verticals. If traditionally they were serviced mostly the smartphones, they are now looking to service new use cases like smart cities, smart homes, connected factories, autonomous factories, connected cars, and more. And these use cases represent different requirements from their network, and more specifically from the base stations. The requirements to support billions of devices, extreme low latency, high-end SLA for always-on applications, security applications, high mobility, and much more capacity are derived down to the base station processing needs. One way to attack this problem is, of course, to build different networks from different applications. The challenge, of course, it's not very scalable to just go and design different networks for any new use case. So what we believe is the solution is centralization and virtualization of the processing. If we could take all the processing, leave the radio distributed, but all the processing, the brain of the network, and centralize it and virtualize it, then we can decide on the fly the amount of capacity we want to provide to each use case. What we want to virtualize when and where. This, as a platform, will enable us to first run and execute the existing airforms of LTE, but then looking into the future, when newer interfaces and waveforms will come, it will be software change. This is the vision. Part of the challenge of actually doing it is when you centralize processing, it means that you need to bring much more pre-processed data into your center location, which means you need fibers, typically. Some of the carriers have challenged because they don't have so many fibers. There are ways to overcome that we will also discuss today in the presentation. So, if we look on the architecture of today's network, it consists mostly of two elements. The very centralized packet core and core center, where the carriers hold the user's information and the cell site information, and management of the users and the cell site, and then a highly distributed cell size with distributed integrated processing. If you look on today processing in the cell site, the base stations consist of radio units and a processing element that it is either integrated, combined in the same box, or it's separated, but it's only virtual separation because the incumbent providers of base stations are always bundle the radio and the processing. The challenge is that carriers would like to introduce clouds and application deeper into the network, closer to the end users. And in order to do that, they are looking to leverage assets they have. They are looking to take the central office they have, which is quite unused today for cellular network. They use it for the wireline. And what the incumbents and ecosystem are proposing to them is take the control plane, the non-real-time elements of the base stations, and put only these elements in the centralized cloud. Why? Because again, if they want to do all the processing in the centralized location, they need fibers, and many times they don't have. Therefore, they suggest take only the control, centralize it. Perhaps you can take some of the gateway function from the packet core, make it deeper into this central office, and now you can run application at the central office. Sounds great. The only problem is you still run into latency issues. If the latency to the traditional packet cores were in the 100 milliseconds, then the latency to the central office is in the 5 to 20. There is still significant latency of bits traveling. And as carriers looking more and more into video type and real-time applications, it will just not be enough. Furthermore, on the cell side, the solution proposed is a highly integrated box with the real-time processing and the RF. This enables continue bundling the end-to-end solution and keeping the network proprietary. Some vendors love it. I doubt about the carriers. The solution ASOCS provide and propose to solve both problems we discussed is open mobile edge clouds and hybrid of an open mobile edge cloud at the very edge before the transport begin that can disable or don't enable to run the processing centralized. The edge cloud role will be to process the real-time processing in a cloud open architecture. After the processing, you can move the data to the more centralized cloud. In the centralized cloud, yes, you can continue and process the control plane and have the application. But we said there is a problem. What happens if the carrier wants to run applications at the very edge, at nearly zero latency after their interface? With this architecture, there is no problem. At the click of the button, I'm demonstrating how a carrier can decide from a single sector to all the sectors which applications they want to run at the edge. At the matter of running all the processing in the open edge cloud unit, they can make it happen. Now, people think, but it's 50-50. If I have edge processing and the centralized processing, where I will take the resources from to now run the complete stack? It's not 50-50. It's more like 95-5. Most of the processing resources are required for the real time, not for the control. So if we have this architecture of mobile edge cloud, open mobile edge cloud, and a centralized cloud, to make a decision to run all the processing at the edge, it's a matter of a click of a button. All the resources are there to enable making it. So, of course, as carriers deploy more and more fibers, and they are, as a strategy actually toward 5G to enable more real-time applications, once there is fiber available between the edge, open mobile edge cloud of certain cell to its adjacent cells, you can create a supercell. This supercell enables you to look on a single cloud and serve multiple cell sites. And of course, as they deploy more fiber directly to the central office itself is becoming the open mobile edge cloud to enable centralization, to enable applications at the true mobile edge, real time, and to enable the ability to run any type of air interface you want, at any time you want. In the specific use case of in-building, you can look on the in-building in a way as a central office for multiple carriers. In large in-buildings, typically there is DAS deployed, distributed antenna system, where the radio is disaggregated from the processing. Radio units of DAS capable to transmit and receive signals for all the carriers in the venue or the enterprise and bring all the pre-processed data into the basement. With direct interface between the digital DAS and the virtual base stations, you can create an end-to-end virtual RAN platform to process data from any carrier of any type of air interface and bring the data directly to application as needed at the very edge of the network. We will focus forward on this use case. So to summarize the first part, in this slide you can see very nice on the top right where the networks are today, where the incumbents are taking them only with a virtualized central cloud with no virtualized edge to keep control the deployments and the carriers, where in the left side you see what ASOCS is proposing for the carriers from a macro networks point of view, to have a hybrid centralized and edge cloud, where the edge cloud, open mobile edge cloud, is capable to run applications at the network edge, and as they deploy more fibers, make the central office your open mobile edge cloud. And again, at the bottom of it is the specific use case of in-building, enterprise, campus, where a lot of capacity is needed, where you have a single network for all the carriers from radio perspective, and ASOCS is working to virtualize these environments. The architecture of the virtual base station in building consists from the left to right with the DAS that provide the radio units to transmit and receive the signals for all the carriers, moving the pre-processed data into basement communication rooms, where you have the DAS point of interface, and then from there, direct interface into the virtual base station point of interface. The virtual base station point of interface holds acceleration resources to be able to transform bits to packets and move the packets into the servers for the software to process the data, the rest of the data. The challenge is that servers today are not optimized for bit processing. So one way is to put way too many server resources to do it, but then you have running into an issue with the business case. ASOCS took a pragmatic approach of leveraging network attached via Ethernet appliance that is radio agnostic. It's not a modem, it's not a base station, it's not a baseband. It is an appliance that hosts resources. It's a server that hosts resources that you can move the bits through these resources, very similar to function chain model, and virtualize a modem via software. The software is the one that defines the flow of bits in the MPU server, modem processor unit server, and define the modem itself. So if the software is LTE, the bits will move between the resources and form an LTE modem. If the software is a new 5G interface, the bits will move in a different way and form a different 5G modem. So this is why this topology represents the first true fully virtualized base station that is capable to support future air interfaces. Whether we call them 5G, 6G, or 10G, we don't really care because we have the platform that can virtualize any modem. From there, the data, of course, going to the packet core, and all of this is managed by a standard NFV, Network Function Virtualization Cloud platform. This was the logical part of the solution. If we look on the physical solution, these virtual machines that runs the virtual base station processing, where are they? If you look on the Open Mobile Edge Cloud, it consists switches to connect, of course, all the elements, Ethernet switches. Then you have the servers that host the Mobile Edge Cloud platform, could be OpenStack, could be other. Then you have the servers for the applications, Mobile Edge applications. These servers can also serve as high availability servers for the virtual base station or the Mobile Edge applications. Then you have, of course, the virtual base station servers. Okay? You can run multiple virtual base stations on every standard off-the-shelf servers that process any type of modem and scale you want, supporting huge amount of users in every single channel and address the capacity need of today and the future. As mentioned, the data, the packets from the virtual base station are traveling via the switch to the MPU, modem processor unit server, that has the hardware acceleration resources inside that transform the packets into bits. These bits will now go via direct interface to the DAS point of interface. The role of the DAS point of interface as a digital router is to be able to define, together with the virtual base station, where these bits should be traveling. Where are the crowded places where we want more of the capacity to go? So this direct interoperability and end-to-end solution enable new features like dynamic capacity routing to address different peak edge that are changing via over time from location to location on the same platform using the same total peak capacity you design in your network. And of course, if you want more capacity, it's only a matter of plugging more resources into your system, like any other cloud scale-out topology. Then, of course, the bits are getting into the DAS remote units, and based on the specific carriers, they either transmit or receive, and going all the way on the other direction. If we look on today's, how the networks are deployed today in building, What you see here on the left is an example of stadiums where you have distributed antenna system remote units all over. I can tell you that in a large Super Bowl event, there might be over 1,000 remote units or radio units in the deployment, and hundreds of sectors for all the carriers. And pretty much every year the amount of capacity is growing, is doubling. So we're really facing a huge exponential growth in terms of capacity needed in this environment. However, in today's topology, to address it, what they do is they take existing base stations that, as mentioned, always coupled with the radio units, and they have to deploy them in the basement. They actually go to the outdoor, they go to the towers, and they take all the equipment in the tower into the basement, and it doesn't fit. They need a lot of space, a lot of power, a lot of air conditioning. It doesn't scale to the amounts they want, and the enterprises pay the price of service as a result of that. What we propose via the direct interface and the virtualization is to transform hundreds of carrier channels into a single rack solution, basically. With direct interface, with full capacity over this, and this number, of course, can double every year as the IT industry is doubling its capability every year. So if it's 100 right now, it will be 200 year after, 400 year after, and so on. This is the way to deal with the capacity growth in large in-building venues and enterprises. To summarize, the benefits on in-building fully virtualized RAN are related to flexibility, modularity, and optimization of the network. The benefits are in all three layers. From a network layer, the introduction of open mobile edge cloud, it's what will enable the carriers to control the network and be able to run the capacity they want in a very efficient way, and enable local application to reside together with the network elements at the edge. At the system layers, the optimized solution with direct interface will bring the solution. And at the processing layer, algorithms to be able to coordinate performance will significantly improve the performance. What you see here is a typical solution where the edge cloud in the enterprise is controlled by the carrier, is owned by the carrier, but this means that now enterprises will bring, instead of proprietary base station, clouds to every major edge. In some cases, it means a lot of CapEx expenditure. What we believe that in certain cases, where the enterprise has a data center already, the enterprise has invested millions of dollars in DAS, they have the DAS, now they need capacity. If the carrier cannot spend the CapEx to bring them the capacity, the enterprise can own it. Using IT and cloud technologies, the carrier can get full control over the performance, the KPIs they want, and the integration to the mother network, or packet core, or the central office. But the CapEx can be on the enterprise, and the enterprise can decide on the level of capacity they want to give to their users. There's a lot of differences in the cloud architecture on the NFV type for carrier own versus a much lighter enterprise own, because enterprise not doing NFV, right? They're doing their own virtualized platform. NFV bring a lot of reliability to the solution, which carrier needs. And again, if the enterprise expects the carrier to bring the solution, this is the architecture will be. If it's enterprise, it can be on a much lighter weight platform. There are pros and cons, of course, to each one of the solutions. And then from a CapEx, of course, NFV would be higher CapEx, but much more higher reliability. And enterprise type could be lower CapEx with, again, lower requirements, because the engineers are inside, they can fix problems on the fly, and so on. Basically, if enterprises has compute, network storage, and some management in the public clouds, at the click of the button now, they can add cellular capacity to the network. These are examples of verticals that can benefit from having distributed antenna system with digital interface to cloud at the edge, not just for the wireless network, cellular network, also for the applications that will be at the edge. These are the type of control and performance benefits, the ability to get huge throughput, security, location-based services, analytics on the fly, and low latency applications like AR/VR, for example. To finish, ASOCS Virtual Base Station and in-building virtual RAN is about setting one platform for all type of networks, for all type of users, enhance the performance of the deployment, future-proof the network investment that carriers and enterprises will do in their networks, and create a multi-vendor solution that drive this. Thank you so much. I hope you enjoyed the presentation and it was beneficial. But if you have any questions.
Yes, please. Thank you, Aaron. Do we have any questions from the floor? I have a question. I
Sure.
knew some people won't ask questions at this time of the day, but I'm
Okay.
not frightened. You talked about dynamic virtualization. To me,
Yes.
that was meaning, I presume, allocating resources or bandwidth dynamically.
Correct.
Who makes the decision?
Okay.
You said
so
with a click of a button, but is
Correct.
it a manual click or is it
it's
software?
not a manual click, actually. So if you look on today automation of the network, there are two types of automation. One automation is on top of the OSS. The OSS look and make decision on physical appliances today. Okay, I'm running out of capacity, I need to put another system into the network.
Yep.
That can remain on adding resources.
Right.
That's a manual work. Someone need to come and put the resources. But once the resources is there, today, the way to automate the service agility is via a function typically residing after the packet core called SON, Self-Organizing Network.
Right.
This SON is quite limited today because it's run from the packet core. Remember the 100 millisecond or so of traveling time. What ASOCS is enabling the platform at the cluster of a virtual base station is to create new algorithms that run faster and control the virtual base station much faster locally at the edge or at the central office. And once you do that, at the click of a software button, basically, or in an automated way, the network can dynamically change itself and make decisions. Now, for some of the decision, the network will make the decision by itself. For some more complicated decision, for example, of shutting down the virtual base station to save on power, the edge self-organizing network algorithm can talk to the centralized one and to ask whether they can get the OSS permission to do that. So all of this will present a new generation of self-organizing networks that can address today's and the future needs in a very efficient manner.
And this goes hand in hand with NFV initiatives as well?
Absolutely. The virtual base station, as I mentioned, is running in an NFV platform at the edge or at the centralized based on the fiber availability. It's controlled by, it's running on whether it's OpenStack or other cloud management system that is NFV compliant or approved by the carrier or the enterprise. And it's really the way to virtualize the networks end-to-end into the future.
And not about time, I think.
We have a demonstration here at the HPE booth, as well as in the Hall 2 E60 where we present a full live network.
There you are. Aaron, thank you very much. Ladies and gentlemen, thank you so much.
Thank you.